Okay, this is the solenoid. So let me send, let me take the, okay, now I'm going to take a rod or say there's a reference, there's the axis here. I'm going to wound a wire on it. There's the axis here. It's like a spring. So this is the axis of solenoid. You can call this as the axis of solenoid. Let me take all to the, this one. Yeah, let's begin now. So here I'm going to send a current which will vary with time, I naught t. Let me stand here. Then how the field will be? Field will be a concentric circles. So we know it should be like a right hand thumb rule. So everywhere the field will be directed like this. This will be the direction of field, no? This one. So even what are that arrow? Arrow indicates the lines of force. So you can show everywhere here. I'll show only at 2 points. Huh? So this will be the lines of force. We have to draw many. I'm showing only few. Okay, no. Yeah. So this is the, it will be here only. I need not to show here. Even the lines of force we have to show since they are owned very close, no? So net field in what direction will be? Inside the solenoid, net field, the direction of net field. The direction of net field, if you're standing here, the net field will be in this direction. B bar. Field produced by the solenoid will be along the axis, will be directed towards left here. Then, okay, let's come for what is the expression for magnetic field inside the solenoid? B equal to mu naught Ni. B is equal to mu naught Ni. And what is small l? Small l is, and N is the number of turns. So this will become mu naught Ni by L. So this is the magnetic field inside the solenoid. Then how many turns are there? N number of turns. So you can count like this. What do you mean by turns? 1, 2. The turns you can count it 1, 2, 3, 4, 5, 6 like this. That will become N. N. What is N? N stands for number of turns here. And L is the physical length, not length of the wire used. Okay, let's come for the any flux linking the each turn. Flux linking each turn. How much it should be equal to B into S, and let this be the radius R, or we'll take it here. So this should be equal to how much? B into pi A square. So this should be mu naught Ni L into pi A square. This is the flux linking each turn. Flux linking the total solenoid. How many turns are there? N turns. So N into this one. So this should be the flux linking each turn. So this will become N into mu naught Ni L pi A square. So I ended up with one equation, mu naught pi A square by L. This is I. Keep it like this. What is the flux linking the solenoid when a current I flows is what we are able to determine. So what is this? This is a flux linking the solenoid. In what direction current I is flowing. So everywhere current is, the arrow indicates. So I'll show specifically like this. So what is this? There's a current I. Black color will indicate the direction of actual current. Okay, no. So this actual current. So what is I? I is the external current. External current flowing in the solenoid. Is that okay? No, this one. No, look at this current. Is it constant or variable? I quote I not a variable current. So then, if I is variable, come for this. If I is variable, B is variable. If B is variable, flux linking each turn variable. Then flux linking the total solenoid is variable. So we'll account to this person. So what he says, flux, negative flux increases d phi by dt. Negative flux increases d phi by dt negative. EMF induced positive. So tell me, like, will there be any induced current in the circuit? Yes, there'll be an induced current. What direction it should be? Account to this person. Account to this person is an observer. Anti-clockwise. So anti-clockwise means in what direction I should push a current? I should bring an induced current in this way. Look at that red color arrows and blue color arrows. They are very important. Where that induced current, it will flow everywhere. Just I'm showing it few places here. What is this? This is strictly. So now what is I? This I high N induced current. The symbols we were using like this, no? This black color arrow and the red color arrow is what? The induced current. Why do this induce current? Due to Lenz's law. Because whenever a flux linking a coil varies, then there must be an induced current should flow that one. According to the Lenz's law, the direction of induced current should be such that it should oppose the cause. What is the cause? I is the cause. And what is the opposition? I induced is the opposition. So therefore, what this coil is trying to do now? It is trying to oppose the varying current. If a current across the coil increases, this coil will try to oppose. So I think instead of showing it many places, I'll show it one place. A thick, big arrow, I'll show it. This is I. And this will be I induced. Or at one place, we'll show like this. This will be I induced. Okay, fine. So this basic concept is very important. The rest of everything you can manage mathematics. It's very easy. Everywhere the current will be flowing, not only in first turn, second turn, at all points in the coil, there will be an induced current. Why do this induced current flows? According to Lenz's law, the direction of induced current should be such that it should oppose the cause. So high in, how it will flow? I in flows opposite to actual current. What about this induced current? It will be far less than I. But altogether, what it is doing, it is trying to oppose. It's trying to oppose that one. So now this particular coil, it is acquired a property. What property? It will oppose varying current. If current across the coil will increase, then it will oppose the increasing current. So this I induced O is produced here. The coil, shall I say that induced current, this induced current the induced current is produced by a solenoid. Got this? This is strictly due to varying current, it is flowing here now. Okay, let's do one thing. I'll send a decreasing current. So if I send a decreasing current, what parameters will come? Let's analyze that condition also. Drawing that. I'll change little bit. Let's see that here. Round turns are needed. Looks very awkward. We'll go back to same earlier method. The same coil, now I'm going to send a decreasing current. So let this be the red color, no? We took. That's what is that red color one? It's only our reference we are drawing it. It's only for our reference we are drawing it. Check it, I think I did nicely. Yeah. Now. So this is about, so now let me send a decreasing current here in this case. A current which will decrease something, I naught minus KT. I should not, as T increases, the magnitude of current will be decreasing that one. Or we'll put like this, I naught 1 plus KT. So in the denominator, as T increases, definitely the value of I will decrease here. So I'll push it in same direction. No, according to the magnetism, so how the lines of force, so everywhere should be. Now also how the magnetic field will be towards left. So I think no, yeah. So what is the net magnetic field will be directed towards left. A person standing here, you will say that the magnetic field is towards left. Now look at the B bar. Again, the same from solenoid equation, B equal to mu naught Ni. I'll not write all everything. So what is the total flux linking? The same formula. So what this person says, the flux is negative. Negative flux. Now what happened? Decreases. Dphi by dt should be positive because current is decreasing. If I decreases, B will decrease. Then what is the flux? Flux equal to B into S. NBS. S is the area of cross section. NB pi A square. So now EMF induced will be negative. So induced current should be negative. So what should be the direction of induced current now? Actual current is flowing like this. This is the direction of actual current. This is the actual current flows like this. You can show at all places. At few places there'll be sufficient. I feel like, you know. No. So this is the actual current. How the induced current? The induced current now, according to Lenz's law, how it should flow? It should flow in the direction of actual current because the direction of induced current suggests it should oppose the cause. What is the cause? Decreasing current. So here the induced current will try to increase it. This is a core idea. I think the previous condition and this condition are totally different here. So how that induced current, red color arrow, it will flow in the direction of induced current. The direction of induced current is such that it will support now the actual current. So now look at the same coil. Earlier when the current was increasing, it was opposing. It will try to decrease it. Now current is decreasing. So what this induced current will do, will try to increase it here. So altogether, what is the property of the coil? It is opposing the varying current. So look at the direction of induced current now towards right now. So therefore, shall I say this coil will behave like a source of EMF, and it is generating what? It is generating an induced current. So at one place only, I'll show it. There's the direction of this one. So this is the actual current, and this is the induced current. So in what direction the coil is trying to push the current in actual flow of actual current. So therefore now I'll give polarity. This end now will become positive. This will be negative. Shall I put like this? Or this end should be positive. This end should be positive, no? This should be negative. Any reason for that? This will act like a source. I can replace directly this within a cell. Sir, how you are replacing this cell? Yes, it is a source of EMF. Then why this end will be positive? Because here the induced current is in this direction. So a positive a current, conventional current should leave positive terminal. So this entire solenoid I can replace with an equivalent cell. Similarly, let me show both the things. Yeah. Similar, look at this one. Similarly here, how the induced current is flowing. The induced current is flowing opposite to actual current. I'll show this. So this is I, this will be I induced. Now, so which end? Now this end I can replace this, the whole everything as, oh, just wait, I'll get it. It got closed. Oh, Everything got erased. This is the technology. Saved it, no? Even after saving it. Uh, I think you have in recording, everything will be there. I'll just draw a rough diagram because again, it takes so much of time, especially that spring, no? It's troubling me a lot. I'll put a rough diagram. It is there. It is there in recording, but not physical copy. Diagrams really troubling a lot. Physics. I'll make it out. Huh? I got an idea, no? So it is like this. Now, what is the current? Current here was. I can't show all in detail. That is the first diagram. Let me copy it. This is a very important thing and it is troubling us. All of you able to see this? Okay, no, we'll continue. So this will be much easier. So in the first case, what is the current? Current was increasing with the time. This one. Here the second case, the current was decreasing with the time, increasing current here. And there's a decreasing current. And already I've come across, so I'll just show only rough diagram. So this is the B bar. The resultant field will be towards left according to the person. Here is the observer. Then what is the actual current? Actual current will flow here like this. And the induced current will flow opposite to that. Why do that induce current? So again, due to Lenz's law. So here actual current will flow towards right and induced current also will be in this direction. Everywhere it should flow, not only at one point, everywhere that one. So what is the black color? This is the actual current. And this is the induced current. So this end now will behave like a cell. This end is behaving like a cell. So this is positive, negative. So I can replace this within a cell of EMF. Now this end will behave like a cell. I can replace with a cell EMF. So this end is positive. This is very important. I'm telling this one. The signs polarity, because all the numerical just revolve around this. Decreasing. So what about actual current? Actual current is flowing like this, and the induced current will flow in the same direction. Sorry, induced current will be like this. So what about here? Actual current is flowing like this. The induced current will flow in this direction. I'll show it here. This is the direction of that polarity with respect to what? With respect to actual current, we are showing it. So therefore, where all this solenoid I can replace with a cell. Now, what is the flux linking? Flux linking, this is like a solenoid. Flux linking, each turn is equal to B into S, which is equal to mu naught Ni into S. So total flux linking the solenoid should be N into flux linking each turn. N into each turn. So this should be called N into mu naught NIS. What is N? Number of turns per unit length. Let L be the length of solenoid. So what is L? L I'll indicate like this here. So let this be the physical length of the solenoid. Okay, fine. So therefore, number of turns, let it be N. So in place of this is N mu naught, this will be N by L, I into, let S be the area of cross section. There's a total flux linking the solenoid. So when I rearrange this, mu naught N square L S into I. What is S? S is the area of cross section. So if you take this radius as A, S will be pi A square. Okay, I think we had a discussion till here. Okay, let me continue now. Now, because of this, it will be like a cell. So now, shall I say one property got obtained? What is one property? What is this coil? What is made up of? Like a conducting wire, copper wire, iron wire. You take any wire, you take any copper, any conducting wire, where a current can flow. Just wound on your finger and make it like a spring. Then pass a varying current. You'll get induced current. So that is simple. Again, don't think something big. Again, so what happened? You take a copper wire. So don't make a spring. Let it be long wire. So the same wire means like there's a wire. Now I'll send a varying current. I'm putting some very important discussion. Please do make observation. I'm sending in a varying current. There's a same wire only. You can see green color. I just took it. Will I get any induced current? No induced current. No induced current. So what is this metal made up of? Copper. So this is also made up of some copper wire. So now this is also same copper wire. Will I get any induced current? No induced current here. Sir, what is this? Because no flux linking the coil. Are you getting no? There's a core idea. So why the same copper wire, you make it like a spring and you send a varying current, then we'll get induced current. So shall I say that the dimensions of coil matters here a lot, the shape of the coil, not like the area of cross section of wire.